All right, I want to make sure that you fully understand what this material is and where it's coming from. And this is why I truly hope you start these lessons right here with Prepare Your Mind. Follow these lessons in this first section because it's really going to help prepare you for not just the material we're going to teach, but how I'm teaching it and why I'm teaching it the way it is. Now, somewhere along the lines, we came up with this idea that programs and projects with large amounts of code were really, really cool and they were awesome. But I want you to understand that this is not really where we want to go today. We're going to learn that lines of code really can affect how healthy a project is, how healthy a team is. And I want to start moving away from being impressed with projects with large amounts of code. If you look at the Linux operating system as an open source project, there's about 24 million lines of code in that project today. That is immense. It's massive. It's going to take a massive team to be able to deal with that. And I personally don't want to be on projects like that. Now here's another thing that I want us to focus on and understand that Go is trying to solve. That we were taught to create these large abstractions in our code base to deal with change. In fact, we've been taught to put abstractions on top of abstractions. This is something that we also need to get rid of because all this is doing is adding more code to our project, which is going to be causing more pain. And I think one of the most beautiful things about Go is that we're going to learn how we can create these very thin layers of decoupling and still achieve our ability to deal with change without all these extra generic layers of abstraction. Now here's another one that a lot of people lose, and it's not fair. The languages you may have been using could have been using a VM like Java and C#, where there's a virtual machine there taking care of what we will call mechanical sympathy. We're going to learn mechanical sympathy in this class. But what's important here is this, is that if performance matters, and it does, that's why we're here using Go, then it's the hardware that matters because it is the hardware that executes instructions. Your performance is going to come from the hardware, nothing else. So we either need to be sympathetic with the hardware or not. The hardware is the platform at the end of the day if performance matters. And we all know that it does. And the last thing here, and again, I think it's lost because of the languages that we've been working with, is that engineering is about understanding cost. Every decision you make comes with a cost. There's a benefit for that decision and a cost. And if the benefit is not outweighing the cost, you shouldn't be taking the decision. You should be making that decision. And so part of this class, a big part of this class is understanding that engineering is about understanding the costs you are taking. And when you don't, you're not coding, you're not engineering, you're hacking. We can't have that today at all. Now, another thing that's very important, these are things that I believe Go is trying to solve. These are problems that Go has seen, and we're trying to solve them with Go. And this other one is that the idea is that you cannot throw more hardware at the problem. Now, not many of us have data centers anymore. We're using the cloud. And so I could apply that to the idea that you can't throw more cloud computing at the problem anymore. It's expensive stuff. And so one of the big things about Go is we're trying to write software that minimizes the use of resources, minimizes the use of that hardware, minimizes the use of cloud. Why? We can keep those costs down. We're on shared machines. And again, all these things are going to tie back in together into the language as we continue to learn it. And we already know this. You can't throw more developers at a problem. At least historically, it hasn't been the case. How many times you've been on a team and a manager, somebody in management comes and says, well, if I throw another developer on this project, could we get it done faster? And I'm always like, look, this isn't accounting. It's not like I can throw an accountant on here and we're going to move faster. This is software development. And there are things that cause us to have pain as a team grows. I think Go is solving a lot of these problems also around package-oriented design. We're going to talk about these things. And there are ways to structure and package projects together where we could put more projects on developers on a team and potentially get more work done. But we have to know and think about this up front, and the language has kind of done that. So throughout this class, throughout the 15 hours that we're going to be together here, I need you to always be a champion for quality, efficiency, and simplicity. I'm going to try to teach you how to do that. It's critically important that you always have a point of view and self-reflect about who you are as a developer. But I don't want you to hold back on your point of view. I want you to analyze and self-reflect. What is my philosophy here? What is driving the engineering decisions that I'm making? Am I improving as a developer? Usually means that you're improving your point of view, that it's changing. It's okay to change your mind on something. That's growth, and we want to have that all the time. So as we continue to focus on this class, I want you to open up your mind. Look, technology is changing quickly. We feel it and see it every day, but our minds change slowly. We resist to change. And it's always easy to adopt new technology, but it's hard to adopt a new way of thinking. And one of the things I got to do in this class is kind of break you down and build you back up. There are things that I'm going to be asking you not to do that you've been doing historically or have been taught to do. Go has different costs for things, and that means that you've got to make different decisions. And it's not that what you were doing before was wrong. It's just that it's not necessarily the best or the right thing to do when we are coding in Go. And these are things that I'm going to try to teach you over the time that we're going to spend together in this class. Now, as we continue to talk about this, I want to focus on this idea of legacy software. If you ever met me in a bar and I've been drinking a little whiskey and you happen to tell me that you're a software developer, well, one of the very first things I'm going to ask you is, what is the legacy you're leaving behind? This is a critical question that you should be asking yourself. Now, I got some really great historical quotes here. I think history is critically important. Mechanics after that, and semantics, behavior. We're going to talk about all of these things throughout the class. But I love this quote from Peter. There are two kinds of software projects, those that fail and those that turn into legacy horrors. This is great. Every time I say it, I crack up a little bit. But it's so true, right? What is a project that fails? A project that fails is a project that never makes it into production. But a project that gets into production and is no longer able to be maintained, that's a legacy horror. And if you really think about it, we've got 40 years of software in this country, around the world, that is really a legacy nightmare. It is. I can't tell you how many times I walk down the street and just wait for the lights to turn off. I'm always saying that I don't want Hollywood anymore to write movies about earthquakes and asteroids. I want a movie about legacy software systematically failing all over the planet and no one being able to do anything about it because there aren't any unit tests to deal with it. And I've got clients today that are writing legacy code out of the box, mainly because one, they don't know how to do it any other way, and two, they create these incredibly short-term milestones for themselves that just really can't be met. And at the end of the day, all they're doing is hacking. Look, Chuck Morse said it best. Legacy software is an unappreciated but serious problem, and it's going to be the downfall of our civilization. I really believe that. But we today have opportunities to learn how to write software that isn't legacy out of the box. Go is at the forefront of this. We just got to learn how to rethink how we do software development, restructure our software development, and keep this in the front of our minds at all times. But I think one of my favorite quotes throughout this entire class and all the material comes from Sarah May. If you don't know Sarah May, you need to look her up. She is a powerhouse, a thought leader in our industry. And though she spends most of her time coding in Ruby, I don't care. What she talks about and the things that she tells us applies to almost any engineering that we're doing in software development. And she said this, and I love this quote: "We think awful code is written by awful devs, but in reality it's written by reasonable devs in awful circumstances." And I want us to understand that because all of us at some point are going to be asked to look at a piece of code that we haven't written. When we look at that code, we might come up with the conclusion that I don't know what kind of drugs this developer was on, but they should have been sharing them because this is out of control. But I want us to step back and think and say, whoa. Let's not trash the developer who wrote this piece of code. Let's come back and ask ourselves, what was the condition or the situation they were in when they had to write this piece of software? And now we're here to maintain it, and maybe we can even improve it. And so I want us to all have empathy for everything that we're doing, because every environment is different, every situation is different, and we're going to be asked also to maintain code that exists. But as you continue to write new code, I want you to think about that person that has to maintain that code after you. That's going to help us move away from these legacy issues. Sarah May, brilliant quote. Now, if we really are going to focus around not creating legacy code out of the box, For me, the number one thing we have to keep in mind are mental models of a code base. Mental models are everything. And it's going to be part of your daily refactoring of the code. Mental models, number one. Now, Tom Love, who's the inventor of Objective-C, said this. And Tom Love works for the Department of Defense on very, very, very large projects. But he said that, let's imagine a project's going to end up with 1 million lines of code or more. The probability of that project being successful, at least in the United States, is about 50%. This is a nasty thought that once projects get over 1 million lines of code, they're probably going to fail. This is scary. But why is Tom saying this? He's saying it because he identified that a ream of copy paper is about 10,000 lines of code. Now put that in your head. I mean, you can all imagine what a ream of copy paper looks like. I'm sure we've all touched a ream at one point or time in our lives. That's 10,000 lines of code. And what Tom is saying is that a developer, the average developer, really can't maintain a mental model of code beyond that 10,000. When we talk about maintaining a mental model, I don't mean memorizing every line of code. What we mean is that you know where everything in that code is. If I ask you where this function is, if I ask you where certain things are, you can find it quickly. You know how the flows work. You know how variables are named. You understand the code base intimately enough where if there is a problem, you could probably go to the code, identify where to start looking, and start reading that code very, very quickly. That's the mental model. This is what we're looking for. And Go is going to allow us to do this because we're going to be able to write less code. But this is really what happens. If the average developer can only handle 10,000 lines of code, then once a project goes beyond 10,000 lines of code, you need a new developer on that project. And when we start talking about code bases with 1 million lines of code, I mean, we're talking about 100 developers on that project if we really want to maintain our mental models and the health of the project. And I don't know about you, but historically, I've only ever worked on teams of about 3 or 4 people. And I could tell you it is difficult to keep 3 or 4 people rowing the boat in the same direction every day. Imagine trying to do that with 100 people. And this is why these projects fail. As the larger the code base gets, it's not even so much a technical issue anymore beyond the fact that we have to manage more people who have to maintain these mental models. We probably don't have even one person that knows the full mental model of that code base. It really becomes both a technical and a management issue. And so we really want to focus on lines of code and reduce it. And to identify the health of our teams, we really need to understand, is there that 10,000 to 1 developer balance? Now, cognitive load is really, really important. And Brian Kernighan said this best. The hardest bugs are those where your mental model of the situation is just wrong because you can't see the problem at all. And everybody knows that debugging a program is twice as hard as writing it. So if you're clever when you write it, how are you going to debug it? People find this really interesting, but historically, I've been writing software for 30 years. Historically, I never allowed developers on my team to use a debugger without asking for permission. And this is primarily because when there is a problem in production, all you have is your mental model of the code base and the logs that you're writing. And if these are not helping you find bugs, you're done, you're lost. You're not going to hook your debugger up into your production environment. And I'm not saying that debuggers are necessarily bad. They are a tool, but they shouldn't be your first tool to finding the bugs. They're great if you've got a brand new code base and you want to understand how it flows. But I have a 20-minute rule, and that 20-minute rule would say leverage your mental models, leverage your logging to find that bug, and if you can't after that, we'll turn it on. But we've got a refactoring problem in front of us at this point because we've lost it. All right, so I don't want us becoming attached to debuggers. I want us to focus on our mental models and really also making sure that we create logs that have more signal to noise. Because I love this quote, debuggers don't remove bugs, they really don't. They just show them in slow motion. At the end of the day, we've got to refactor that code cleanly so those bugs disappear. But at the same time, if more bugs start to show, I don't need to waste time on the debugger. Our mental models, our logging, it all helps.